Welcome to the second law of thermodynamics. Today, we will be calculating entropy. The first two methods had already been discussed, therefore we will look into entropy associated with phase change. First, let's derive the equation that we will be using. So delta S is equal to delta Q over T. And the formula for Q that is associated with phase change could be your mHv or mHf, wherein Hv and Hf are your heat of vaporization or your heat of fusion. That is also commonly termed as your enthalpy of vaporization or your enthalpy of fusion. Therefore, we will substitute this value on our general equation at the top. Therefore, this will be delta S is equal to mHv over T. However, Hv is interchangeable with Hf, whichever is required by the problem, and m is also interchangeable with your n, which is the number of moles. Let's calculate using this problem. 1 mole of substance A is vaporized at 100 degrees Celsius with a heat of vaporization of 40.7 kilojoules per mole. What is the molar entropy of vaporization? Let's write our given. Temperature is 100 degrees Celsius. Heat of vaporization is 40.7 kilojoules per mole. So the appropriate formula to use is delta S is equal to NHV per T. But this time we are asked for the molar entropy, therefore we don't need to add your N. Divided by our temperature, which is 100 degrees Celsius. But let's convert this to Kelvin. So let's add 273.15. What will be our delta S? Delta S is 0.1091 kilojoules mole Kelvin. Did you get this value? For our next problem, we will be combining entropy calculation dependent with time and entropy calculation associated with phase change. First, let's analyze our problem. We have water at 353 Kelvin. So this is still liquid. And then the end point is 403 Kelvin. And this is already gaseous since it passed the boiling point of water. At this point, this is gas. Therefore, there will be three changes associated with this heating. The first change that we have is a change in temperature. So this is the boiling point of water, and at this point, we still have a liquid. And then phase change will occur, still at 373 Kelvin, but you already have your gas. And finally, the last change is another increase in temperature from 373 to 403 Kelvin, still at the same phase, which is gas. Let's do our first calculation. The appropriate formula to use is delta S is equal to N Cp ln of T2 over T1. So delta S is equal to 1 mole times our Cp, which is 75.3, ln of T2, which is 373, divided by 353. Let's write the equation for the second change. This will be delta S is equal to NHV per T. This will be delta S is equal to 1 mole times HV, which is 4.07 times 10 raised to 4 divided by 373 Kelvin. And for our last change, it is just like the first one. So it's 1 times 36.4 ln of 403 divided by 353. in Kelvin. So let's calculate for these values. For this first change, we have an enthalpy of 4.1498 joules per Kelvin. For our second change over here, we have 4.07 times 10 raised to 4 divided by 373. So that is 109.1153 joules per Kelvin. And for our last change, delta S will be equal to 2.8158 joules per Kelvin. So are these your final answers? No, because we are asked to compute or to calculate for the entropy change after heating it from 353 to 403. So this will be delta S total is equal to 4.1498 plus 109.1153 plus 2.8158. So delta S total will be equal to, so this will be equal to 116.0809 joules per Kelvin. Let's summarize all of the formulas that we have studied. So delta S is equal to the S of your products minus the S of your reactants. Entropy's dependence on temperature is illustrated by delta S is equal to mCp ln of T2 over T1. And finally, entropy associated with phase change is delta S is equal to mH over your temperature. So that's it for this video. Thank you, and you may post your questions on the comment section below.